mathematics and perspectives. So I guess I have to say that the team is very young. We have been working mainly on fairness and interpretability, and recently we started working on stability issues. The team has both computational researchers and mathematics researchers. So I come from mathematical side, so I like proofs most of the time, and interestingly enough, I do proofs, but there are people who do also computation-based science. Let me tell the disclaimer that the presentation represents the views of the office and does not indicate concurrence by Discover Financial Services. So everything I say is essentially opinion of mine and the co-authors. So the kind of quick overview. So I will get you a little bit into fairness. Some of you may or may not have seen this topic. I'll discuss fairness for classifiers and the issues that arise. But in the end, we are not interested in classifiers, rather we're interested in fairness at the level of a distribution with the control of the distribution. So everything I say will be relevant for both classification scores or regressors in general. So then I will introduce model bias metrics. I will give you a couple of slides on interpretability of machine learning models, but it's mainly just sort of a review of what exists. And then I'll get into the fairness interpretability. Okay, so let me start with the introduction. So why do we care at Discover? So Discover is a bank. We also have a credit card. And of course, we use predictive machine learning models for various purposes. The predictive models and also the strategies that rely on these models, they're subject to laws and regulations that ensure fairness. And so, for example, ECOA and EOA, these are Employment Opportunity Acts, essentially Fair Lending Act, etc. There are many regulations that ensure fairness. We have to comply with these regulations. The machine learning a model that produces a risk score, right? It might essentially be discriminatory in terms of the outcomes towards certain protected attributes. And by a protected attribute, I mean, for example, race, gender, age, ethnicity, national origin, mental status, etc. And regulations sort of prohibit discrimination or prohibit a large bias or discriminatory outcomes. So we have to monitor that within the models. We have to mitigate the unfairness. So this is basically the motivation for the topic. And of course, there's always a trade-off between accuracy and bias, and we need to understand what it is and how to mitigate these trade-offs. So what will be the machine learning fairness steps in principle in industry? And there are two simple steps. Step number one, you try to assess the fairness of your machine learning model. Once you understand step number two, you may try to actually mitigate the unfairness or bias mitigation. The word bias could be abused. It has nothing to do with a statistical bias. It's more or less the measure of unfairness. So kind of, please be aware of that. I will get to math eventually, but I try to filter out the math parts and leave most of the fun parts. So, now there is a little bit of notation. So I start with classification only for one reason. The classifiers, they are fundamental blocks for what's happening in the model. Because if I give you any regressor, I can always by holding data classifiers, right? So in some sense, let me not differentiate between classification and a regular regression, because I can get a bunch of classifiers out of any regressor I want, right? Just by thresholding. So let me start with classification. but then we will move off to regressors, and everything I say is applicable to general regression problems, all classification scores which are regressors. Well, for notation, basically, we have a triple X, which stands for predictors, G that stands for the protected attribute, for example, male, female, and Y stands for response variable. In principle, it could be any variable which is continuous, mixed, doesn't matter, but I will start with Y, which only takes two values, 0, 1. Okay, for example, 1 could be higher, 0 is not higher. The 1 could be will return, sort of a loan, or will not return a loan, etc. So for the models, so the f of x stands for a general classification score function. It's a trained classification score. Thresholding, it doesn't have to be again a classification score. It could be just a regular regressor if we change the y to be continuous. The YT stands for a threshold classifiers, parameterized by a threshold, and y hat is just a classifier. We will assume again for the talk that the G equals 0 is kind of a non-protected class, which is typically a majority class. For example, males could be a non-protected class, and then you can look and assess unfairness with respect to minority groups with respect to this big class. Right? For example, white males. And also you have to decide what's a favorable outcome. Is it 1 or 0? Just for the duration of the talk, I assume the favorable outcome is y equals 0. So I used to think in terms of risk scores. For not returning a loan, 1 sort of, right, is a negative thing to me. And 0 is good. So it's a favorable outcome. Once you decide on what the favorable outcome is, well, we can kind of move on and ask ourselves, okay, suppose first I'm really focused on classifiers. What are available fairness criteria? Something that's off the shelf, something that's available and has been discussed by many people. And of course, for example, Feldman and his colleagues, introduced statistical parity for classifiers, right? So what it requires the probability, right, of your trained classifier to be given 0 in the first class and the second coincide. That is basically proportions of people who've been labeled by your model 0 for males and females are the same. This is a statistical measure, right? You're just looking at proportions. That's it. Pretty simple. Then there are other things such as equalized odds introduced by Hart et al. It's Maurice Hart. He also works with Feldman with Tinker work. If you're familiar with the works of Tinker work, which was also one of the main authors in the fairness area. And the equalized odds are slightly different, and it requires that the individuals who are labeled by your model as 0 in the first group and the second are classified the same given you also conditioned on the true value of the y. That is, basically you want misclassification in both groups to be the same for both values of y, whether 0 or 1. And equal opportunity only requires that for the favorable outcome. If you want to classify somebody as will return a loan, you would like the proportions among the groups where you guess the classification correctly, right? These proportions to be the same. It has to be noted that statistical parity and equal odds are not compatible. It's been known, and Maurice Hart talks about that. So these notions, right, you can't put them together as constraints. They are very different, and it's easy to show an example where they will never, you cannot require both of them simultaneously. Well, when we thought about that, we came to the realization that, look, it's of course all great to look at proportions, but since we were interested more or less in the distribution of a classification score, rather than just classifier obtained by thresholding, it came to mind to look at values? Why do I want to only look at proportions? I'll give you a picture, an example soon. But I want to look at the values themselves, not proportions. And you can require geometric parity. And geometric parity requires that if you take a non-protected class 0, if you look at its CDF, for example, and you ask me for the given quantile P star, whether the values for the first subpopulation and the second are equal, then for that given threshold T, you get the geometric parity. So instead of proportions, it looks at quantiles, and you are requiring the quantiles to be the same. You may say, oh, of course, but isn't that the same? Of course, when you have continuous random variables, statistical parity and geometric parity become the same. If you have PDFs for both random variables that have support, which is connected, then it is the same, but it's not in general the same. And it brings an important point. Shouldn't we look at the values? Okay, so maybe first just a simple naive. All examples are very instructive and simple. I did it on purpose just to get the point across faster. So let's say I look at a very simple model where I have a predictor, and the variable G, think of that as, for example, G equals 0 is males and G equals 1 is females. And the two distributions for the predictor, two subpopulation distributions, are different for males and females. So if I train a classifier, or if I just discover, what would I discover if I train not a classifier but rather a classification model? Right? You get the score. The y is just Bernoulli f of x, where f of x is just a logistic 5 minus x. So the score itself does not depend on the protected attribute G, but predictors do. And so by essentially the model, right, learns from the proxy predictor who is who, and starts basically producing different proportions in terms of outcomes. So if you look on the picture on the right, and you ask yourself, okay, let me measure the statistical parity as the threshold over here on the bottom changes. So I'm thresholding my classifier and I change the threshold, and I want to look at what happens with the difference between proportions. So as you see, basically, this is the balanced error. So as your error decreases, you get bigger and bigger difference in statistical parity. So which means that the better your performance, the more biased it is in statistical parity metric. But similar situations happens with equalized odds. All right, essentially it's the flipped U-shaped picture. Thus, there is a trade-off between accuracy and bias. Again, it's been known for quite some time that as you try to put as a constraint any fairness metric to minimize, your performance will decrease. Right? Because the fairness means that you can differentiate between two subpopulation distributions. If that difference was in data, the machine learning will learn. So if you want in a certain method, whether it's statistical parity or anything else, to be fair, right, you have to put it as a constraint, and you have to play a game by reducing performance, give a little bit of fairness. You can't have fairness and best performance in general. Okay, so what are the fairness? What's available? Let me kind of quickly tell you what's available. Some approaches for bias mitigation, right? If I constructed the classification score with the formula which looks like Bernoulli f of x, right? What would I do if I want to mitigate the bias? So there is a maximization with fairness constraints. That's a typical approach. You design a classifier that depends on both x and g. You can either think of that as a maximization technique or minimization with a fairness constraint, or you can use a min-max approach. As basically, you can have a collection of metrics metrics computes the fairness and performance. Then you change the metric, you try to achieve, think of the fairness as a penalization. You change the metric once you minimize a certain function, and then you check it again. And so the minimax essentially goes back and forth between two different types of metrics and tries to find, maybe I overfitted, and then you change the metric and you try from another angle, right? You don't want overfitting. But it's all the same. It's just a minimization given the fairness constraint. There are other methods. For example, the Hub describes post-processed method, which given already trained model, it designs a post-processed model by introducing some randomness into it. Statistical parity does not require randomness, but equalized odds or equal opportunity, you have to introduce a little bit of randomness when you make a decision, otherwise you cannot achieve the parity. There is a method of Feldman which says, okay, why don't we just go and massage a little bit data, and we introduce some massaging of predictors, and we change them, make more fair predictors themselves, so that the outcomes will be fair too, and it works. It requires lots of effort, and it's not always actually best because the data could be very big. Transformations that discussed in the paper might not be, always realizable. And there are other methods such as Pareto efficient frontier. For example, Nick Schmidt and Stephens, they have been discussing and saying, look, if you have a collection of models, right? If this is bias and this is loss, we can put all of those models and essentially justify picking a model that's on the frontier rather than a model in between. And that approach basically complies with the regulations, because if you already have trained the models and you plotted that on the bias and loss frontier after training, then first of all, you don't give modelers access to the protected attribute, which lie lower is impossible to have. This is another thing that will pop up. But the Perron et al., this is, I think, maybe Amazon's team, I'm not sure, but they said, okay, fine, why don't we try to take a machine learning model, think of its parameters as a space, and we will keep searching using hyperparameter search. Well, this is a good thing to do. It's very elegant. There are a couple of things that I have to say. Of course, the training on a lot of models is expensive. Doing hyperparameter search, you have to be careful, because hyperparameter search involves a process. And as you evolve the process and you search, you use what you right. You use information from before. So I can overfit, right? That's something to have in mind. You can't just say, oh, here it is. You have to be careful. But that is a technical issue, right? Overfitting. You can design, for example, use a reusable holdout. The simply at work and characteristics so that they reuse the reusable holdout, or you can reuse the same validation set with introduction of a little bit of noise to avoid overfitting, and it's within the data privacy framework. Now, the explicit use of the protected attribute G is not allowed by ECOA, neither in training, no prediction. So that is the motivation for what we are doing in our team. We cannot use the data for whether you're male or female. We can't have this data. First of all, we don't have it. Second of all, we're not allowed to have it. We can't have this data neither for prediction nor in training. These data only available for fairness assessment in between. That's step number one. So anything you say, oh, why don't we just use minimization? I can't do it. We can't do it. I can't say minimization. Why? I don't have G. Go figure. But I can't make it fair. So the typical bias measurements test fairness of a classifier, not the regressive score. The truth is, many decisions and strategies do not rely only on a classifier. They may rely on the whole classification score. The classification score are probabilities. So you need a distribution. And that is why I want to make fair the whole distribution, not just one classifier. And of course, the mitigation procedures also often focus on a classification, on a classifier, not the regressor. And of course, using hyperparameter search in the Pareto frontier to construct the Pareto frontier, it is very computationally expensive. The data, as I've learned, could be so large. Copying them takes weeks, from one machine to the other. And that is not nice. So retraining something like this would be really time consuming, right? And of course, we also would like to understand within different metrics, what are the main drivers of the model bias in our data? And how do we do that? Right, so what is the acceptable form of bias mitigation that would be fine, that would be okay with regulations? And in general, that would be sort of realizable in practice. So first of all, given a regressor model, we would like, after training, to understand what the bias is between across the subpopulation distributions of f of x given g equals k. For k, it could be 0, 1, 2, 3, but I will work with two classes. So I want to understand what's the bias. So I need to come up with an appropriate metric. Number two, I want to determine the main drivers given the fairness metric. And of course, I want to construct, for example, a post-process model that does not rely on G, and that will be done within the fairness assessment, within a fairness assessment window between prediction and the training. So the resulting model just depends on X. And the post-process model essentially could be used by simple techniques to construct a fairer model where fairness is assessed at the level of the distribution, and we can pick those models that we like to use and then pass it to the prediction stage. So that would be acceptable. And I will be talking only about the step number 1 and 2. Number 3, we worked out all of the details, and it works really nice. But until we publish the paper, I don't want to talk about it, and it will happen probably in about a month or so. The paper for the second part will be there. We use part 1 and 2 in order to do 3. And part 1 and 2 for me is a real fun. Okay, so model bias metrics for regressors. Right, so now we've just talked about classifiers. But let's jump and think of regressors or classification scores, which are regressors. All my examples are for classification scores. So at an algorithmic level, the bias can be viewed as an ability to differentiate between two subpopulations at the level of data or outcomes. This is just directly copied from my paper. But the idea, I have to say, of course, came from the paper of Edward because she basically rephrased some of the thoughts. Right. So let me tell you about the metrics requirement, but then explain why the requirements are like that. So the metric must keep track of the geometry of the model distribution. So this is a push-forward measure, a P of the regressor of X. It must be consistent with the wide class of classifier fairness criteria. As I said, any regressor can be turned into classifiers by thresholding. So if I have certain parity, can I marry the two perspectives? The fairness at the level of distributions and probability measures and those parity of classifiers. Yes, it's not difficult, you can. Number 3, we must keep track of the sign of the bias across the population. I want to understand whether the model favors protected group like males or disfavors or both. It shouldn't be just a number. There's more information in the fairness. You have to understand what does it mean. We mostly favor, we mostly disfavor, how much. And it must be meaningful because we would like to explain that number, right? It has to have some kind of meaning, at least for us. And I want to make the following detour, which is the main objective of which to explain why I care about the geometry. So an ability to differentiate versus independence or dependence. Suppose I give you a regressor which has a really weird distribution. It has two subpopulation distributions. One is at Z0, another at Z0 plus epsilon. Think of that is just a regressor. It has only 2 points. So the CDFs of such a regressor, right, will be two bounds. One at x0, as you know, another at z0 plus epsilon. So no matter how much I move things to each other, you can always differentiate. If I give you the whether you're male or female, I can always tell you which value of the regressor you get. And the mutual information will tell you that it doesn't change no matter what epsilon is. I can move them as close as I like. Now let me switch to and tell you this is an income, for example, of females. This is an income, for example, of males or vice versa. If I move them, and z0 is, I don't know, 100K, and z0 plus epsilon, and epsilon is the same. If I keep decreasing epsilon to almost 0, will it get fairer? So I'm looking at the values. Seems to me, yes. Now let's look from the perspective of statistical parity. Remember, I said I can threshold at any classifier. So let me put a threshold over here and ask myself if these were probability measures, subpopulation distribution of your classification score. If I take any threshold for such score on the right or on the left, statistical parity will be achieved. But if I take it in between, statistical parity will tell you the difference is 100%. Well, now, so the next question is, okay, I still can differentiate, but it seems to me by moving the two data measures together, I make things fairer. So if the ability to differentiate can result in unfair outcomes, if you make things fairer, it does not necessarily mean that things are independent and you cannot differentiate. That's something that became a realization to me. And it was more conceptual. I was like, oh, really? So that is why we decided that, look, we want to make values fairer, not proportions. And you say, well, but what if you pick the classifier or a thresholding over here, then statistical parity will not be achieved. But I'm looking at the distribution fairness, not a classifier. What if by sacrificing a small epsilon measure set of thresholds and throwing it away, I can make on average the model fairer? It's just you won't be able to use those thresholds at the prediction level. So that's why I'm interested in values rather than proportions. So what are the candidates for metrics that really look at the geometry? So one of them is the randomized binary classifier developed by Borg. I won't get into that, but it essentially says, okay, I will look at the randomized classifier that maps values from a certain metric space Z equipped with a metric between 2 points into the outcomes 0 and 1. Right? These randomized classifiers are maps, and you will drop them onto your distribution, and you will vary Z as a distribution 1 and Z as a distribution 2, and you will look and you ask, can you please differentiate between these two distributions? So the classifiers are basically like trained animals. They jump and they try to differentiate. And then you take supremum over it. That's one approach. We quickly learned that it's nice. It has the values of the bias 0, 1, but it has problems with scalability. I won't get into that. The point being that we kind of said, look, first of all, Cynthia's work did establish the connection between randomized classifier and the Wasserstein distance. Wasserstein distance, computes the transport effort of one distribution into the other, not necessarily continuous, by essentially computing the infimum over all transport plans, which are joint probability measures, whose marginal distributions is distribution 1 and distribution 2, right? So this is the definition of the Wasserstein method. So this has a much better property in terms of scalability. Classification score is because it's a regressor, always lives in 0, 1. So you can just use Wasserstein. For regressors that have values outside of 0, 1, it's really easy to handle the issue, but you can get the metric that measures the distance between two subpopulation distributions to live happily ever after in 0, 1 and have scalability property. But this metric doesn't have a scalability, and that's kind of problematic. So in our case, distribution mu1 is typically joint probability measure of the score, because this is your response, given G equals 0, and mu2 is the same, G equals 1. So we chose to work with the Wasserstein metric. This is the relationship of the bias and the Wasserstein metric. As long as your metric on the space of points D is less than 1, there's an equality. It's not always the case. Unfortunately, we would like to work with increasing metrics. So in principle, you can apply and get the connection with something that lives outside of the unit ball. And there's a connection of the two metrics which we established, which is not very difficult. But the main point is, here is what happens. Suppose you have two distributions and you're looking at the blue and the red one in the continuous case. So if I compute the Wasserstein metric with Q equal 1, then the transport effort is just the area between the two curves. Now you can explicitly write down in the case of continuous random variables what the transport plan is, what the joint probability measure is that transports one distribution into the other. It's very, very easy, right? And it's a solution of a longer transport problem. When you have jumps, etc., I can just easily draw. Again, it's not difficult to write down the pi, the transport distribution. But the point being that you can have with transport, you can discover the flow. When you're transporting, let's say, a protected group into non-protected, you can discover whether you are transporting in favorable direction or not in favorable. And suddenly things make sense. You can say, aha, I'm not just measuring bias by computing the area. I can A, compute the flow, and B, I can know which quantiles of populations for protected attribute travel towards favorable direction and which are not. It's a very useful information as it turns out. To kind of fact, again, maybe I'll skip the first one. The second one, given predictors X and model F, we define the bias as the Wasserstein distance between two probability measures. One is the probability measure corresponding to the subpopulation of the regressor for the class 0, and the other for the class 1. As I said, if your regressor is outside of the unit interval, it's easy to fix. What's the connection with statistical parity? Well, in fact, if you take out of f of x and you construct by thresholding a classifier, the Wasserstein bias is just an integrated statistical parity bias. So that means you can actually cook up any metric for classifiers, equalize dot, equalize parity, and then cook up a Wasserstein-based metric that for each threshold essentially gives you the metric you like. So if you have some kind of sets, events, A1, A2, AM, like in equalized dots, and you require the generic parity condition, the Wasserstein-based bias could be cooked up as a weighted metric where you incorporate Y integration of classifiers given those events. Right, so it gives you a huge family of metrics, and you can live within this transport. It's not just statistical parity. You can hook up any metric you want and use it in the process. Now, though we start with quantiles, you can easily jump to thresholds because you can invert the quantile functions and you can make them CDFs, and that's been known for ages. Of course, it's very easy to take as a graduate on the graduate exercise. Okay, so basically the model bias metrics, right? Let me kind of have an example, right? This is an actual example where I have a simple model with one predictor, x given g equals 0 and x given g equals 1. Here, the two predictors have the same expectation. So if you just say, oh, measure fairness by looking at expectations, that's not nice. Look, expectations coincide, variances are different. So if I look at the classification score, then you'll see that there will be quantiles for which I favor non-protected class, and there will be quantiles for which I favor non-protected class. You can measure both of these parts, and that gives you positive and negative model biases at the level of distribution, where you compute those essentially areas. So, but once I got those numbers, I want to mitigate the bias. And so I want to know not only the model bias, I want to know not only the decomposition, the positive and negative part, I want to try to explain which predictor mostly impacts. Because if I know that, I can cook out a post-processing procedure that essentially targets the reduction of the model bias. So very quickly, sort of on interpretability, there's probably like 6 minutes left. So in terms of interpretability, first you can you ask yourself, okay, if I just want to explain the model itself, not fairness, available simple things that have been known for quite some time, of course, let's say marginal expectation of a function given a predictor, right? If you condition, you get a conditional expectation. You can say, okay, if I condition a Wilmer generalization, I can try to explain the impact of predictor on the model. And this is what, 2001. Now there is a more sophisticated tools such as game theory. So you have n predictors, so you want to explain the value f of x of your model. One way of thinking of that is using predictors as players. 1, 2, 3 up to n denote players. Then use a certain function which is called a game. It's a set function, typically superadditive, which is plays on the players. And S here is any set of a coalition of players. And the game value is nothing but an operation or an operator that acts on those games, and you can sum up the game's linear operation. It would be a linear operation. And returns you n values. Those n values are contribution of each player. Meanwhile, V of n is called the total payoff. It's total payoff of the game. So the Shapley value has been introduced by Shapley in 1953. It became very, very popular in the past decade and before. So the Shapley value is very special because it has a nice property called efficiency. If you compute contribution of each player, it sums up to be precisely to be the payoff. It's linear, it's symmetric. That means you can players are abstract. You can index them as you like. Okay, well, what is the game? Well, there are two typical games to use in that business: the marginal game and a conditional game. So by giving a collection of players, I can condition on them, and it gives you a value. That's the game. It's not superadditive, but you can use it as a game. Then you can compute the Shapley value. So these are the typical ways to explain. This is just a picture. So what is an explanation of a model? Is it a number? I don't think about it as a number. Why? Because your predictors are probabilistic, right? They have a distribution. So if I compute the explanation for each value of the predictor, you get a distribution. So this is how we look for a very simple baby model. And I'm just explaining a simple model, which is a product. These are predictors, and this axis is an explanation. The black dots are projected data. So this is data versus explanation. So that's something, again, has been known for quite some time. So what is the fairness interpretability? Can we explore that? Right, so my point being here is that you have to think about explanations as random variables. They're not numbers, right? Because people say, what's the explanation for that individual? 0.3. What will I do with that, right? Not much. It's good for the individual to know. Although, other than that, if I want to try to explain fairness, it's not good enough for me. I need to know, how they vary across the data set, right? So I will be using these distributions to explain fairness. So imagine first I give you an abstract explainer function EI that explains the ith predictor of the model F. What I can do, I can look at the distribution of that explainer of given that you come from class 0 and given that you come from class 1, and I can measure the Wasserstein distance. Very simplistic, right? There's nothing difficult here. And this is the beta I that gives you a collection of explanations. These are numbers. And we call them bias explanations. Of course, you can only measure the distance. You can measure also the flow. Since you have a favorable outcome, you can also measure positive and negative explanations by doing exactly the same what we've done with model bias. So you can understand what's the impact to the positive flow and to the negative flow. So this is a simple example. The first picture shows you the model and its distribution. So you can see that it is positively biased because in my case, I'm working with a risk score. So anything to the left is less risky. So I'm favoring the non-protected positive. But what happens if I take a simple, Shapley value and I compute the same distances? What happens? These next 5 pictures for the model with 5 predictors actually show you the distributions for explanation, and then I compute positive and negative values over here. So it gives me essentially a diagram where I can tell you how much, right, I contribute as a predictor to moving parts, right, to a favoring and how much to disfavoring. This is extremely helpful in bias mitigation because, believe it or not, when you have 500 predictors, you may end up with just 6 most impactful. So it reduces the dimension from 500 to 5. That's a lot. And I can then run that on my laptop literally within an hour. With 500, I can't do it. I have to do it on the cloud and it takes forever. Right? So that is helpful, but of course it has drawbacks because it's not very clever. Right? Well, you computed marginal explanation and you looked at the bias. Right? So how hard could it be? The other thing that there are other issues, for example, with that is the bias explanations for these 2 models, number 1 and number 2, and here are the same. Observe, in the second picture, the model bias is 0. And when I add up 2 predictors, they interact and destroy bias of each other because across these 2 quantiles and these 2 quantiles, when you interact, it goes away. But on that picture, the bias explanations are exactly as below. But when you put them together in the model, you end up with actually much bigger bias. So these explanations do not care where the mass is transported from. Right, so it is very reduced information you're getting. So is there any solution to that? In fact, yes, you can, and I need another 30 seconds and we're done. I guess a bigger picture. So now I say, okay, I have these players, right, and predictors. And I can ask myself the following question. What if those players join in certain types of coalitions when they are together? When let's say I pair up predictor 1 and 2 or 1, 2, and 3. If they join that coalition, what would be the bias just caused by these 3? If I can do that for any coalition, then I can design a game. What is this game? It's a bias game. And the bias game, given a set S of predictors, I can look at the Wasserstein distance between the subpopulation distributions of an explainer that must explain the whole collection. Important note, of course, explanations or explainers that you are using matter a lot. Why? What are you trying to explain? Are you trying to explain a bias in data? Are you trying to explain the bias in the model, right? That is something we have to keep in mind. But for now, let me just describe the process. So you gave me this explainer and I designed the game. Now I compute So some coalitions would push distributions together, and some push them, push them apart, and some push them together. So by playing this game, you can compute the Shapley explanation of that game. Unlike the basic bias explanations, for example, here on the left, on the right, this is a total and a net bias. You can play a game, and if you look at the yellow lines, without any introduction, any signs of a bias, you can just look at the total bias. It will discover that explanations could become negative. It can discover which predictors are mostly favored and which are mostly disfavored. But you can play the same game with the positive and negative parts too. There is a meaning for the negative and positive, but I'll leave it to the paper to read. It's there. These types of explanations track more information about the populations in terms of quantiles and keep track of how the mass is moving. So it's a bit more informative, and more or less, it's additive. So the sums of positive explanations and sum of negative Shapley explanations together will give you Shapley explanations of the total bias. So everything is linear. It's very easy to prove. And I guess maybe the final slide would be this. You can say, what if I change the explainer and I play the game, which is based on conditional expectation? Then you can explain the data, and it gives you stability in the norm under the push forward of the drawing distribution X. And what if I play in a marginal game? Because playing a conditional game is very difficult. Marginal game is easy to compute, it's just averaging. Well, unfortunately, you get stable, but not in a database metric. We came up with this metric. You will be stable in this metric, comprised of all these different products. And that is why there will be no surprise. Once you change the model that has exactly the same outcome, your bias explanations based on the marginal game will change. You have to be very careful, right? Do you want to understand the model? Or you want to understand the data? And there is a difference. We want to understand the model for one reason only, because bias mitigation needs to modify and post-process the model. But in general, the first one is also kind of is of interest. I think there is something on stability in another paper of ours, and it covers this topic. This is a technical topic, and we prove instabilities and blowing up solutions and blowing up explanations. So kind of one has to be really, really careful about that. And the proof is in the paper number 2. I have to acknowledge all the people, our Steve Dickerson and Raul Kulkarni. So they kind of helped us and really directed us in terms of the industry, and the rest of the people from compliance department and professors who helped us. So, well, basically I'm done. Thank you very much.
So are there any questions? I'll ask a question. Can you go back to the stability?
Yes.
So here, can you motivate a little bit why you call such bound as stability bounds, and how do they translate into what you're interested in?
Okay. Yes, you can. Maybe you have to start first with a regular explanation, right? So if you view explanations as random variables and use game theoretical approach, so then you design an operator. And this operator maps essentially functions or models into explanations which are random variable. This operator is linear because Shapley value and other game theoretical, game values which we're using are linear. And so the question arises, right? The next step is to choose the domain for the operator. So then you ask yourself, what is the domain in which this is stable? This is essentially on the second line is the smallest domain for which the operator that we design will be bounded. Otherwise, it becomes unbounded. And hence, for models that in the metric on the line number 1 are slightly different, you have infinitely large essentially differences in explanation. So you can easily design extremely catastrophic scenarios where things are very, very different. So now it doesn't mean that it's bad. It just says that in that metric it's unstable. And we are motivated because you can ask yourself, okay, if I retrain the model and it gives absolutely the same result as the one I did yesterday, like the same, 100%, will I get different explanations? The answer is yes, absolutely different. And that leads you to question the stability. But it's because you used the metric, right? The metric in number one is a database metric. And you say, well, how can I make the marginal explanation stable? It's because you were looking at the different metric. That's the metric. There's a much finer topology, right, from the topological standpoint of view. And so this is the smallest, I think, topology in which things are continuous. Once you turn to metric number one, things go up. And the same is true for any other games which somehow employ probability. For example, like you can look at the interventional probabilities, right? You can look at dependencies. So essentially the difference between the two pops up when you have dependence and predictors. When there's no dependence, of course, marginal conditional will agree. But the dependencies are there and they will cause havoc. And you will be surprised. Why today I'm getting absolutely different picture? It is, even though the model is like this has the same quality as the previous one. There is a way to marry the 2 points of view through design of certain games. And we handle that and we prove theoretically, if you properly do grouping, you can make them equal, but it requires to group by independence. And you have to have some kind of assessment of mutual information between the groups to ensure that you properly group, otherwise you won't marry the two. And it's kind of funny. You have unstable things, you just sum up and they suddenly become stable. And that's an interesting thing. Right? But you sum up in an appropriate way, like not just sum up.
Group in the right way.
Yeah. Did I explain that?
Yes.
The same things, of course, happens here, but the operators are non-linear.
Any other questions? If not, let's have Alexey again. Thank you very much.
Thank you.